So problem B is a construction company has an expenditure rate of EX equals E to the 0.17x dollars per day on a particular paving job, and an income rate of IX equals 120.6 minus E to the 0.17x dollars per day on the same job, where X is the number of days from the start of the job. The company's profit on that job will equal total income less total expenditures. Profit will be maximized if the job ends at the optimum time, which is the point where the two curves meet. So I just want to go over some of the equations before we dive right into the problem. So from 15.1, we will be using the antiderivative for exponential functions equations, which is e to the ax equals 1 over a times e to the ax. We're using the sum and difference rule, which is the antiderivative of f of x plus g of x equals the antiderivative of f of x plus the antiderivative of g of x. And we'll be using the constant multiple rule, which is k times f of x equals k times the antiderivative of f of x. And lastly, from 15.5, we'll be using the new equation we learned of the upper bound, which is b times a, which are above and below the antiderivative, of the upper function minus the upper and lower bound antiderivative of the lower function. And b will be greater than a. So to do this, you will just plug in b for x and a from x and subtract the two numbers. So the start of this problem is a, which is to find the optimum number of days for the job to last. So for this problem, we will be using both equations, e to the x and I to the x, and we will actually set them equal to each other. So e to the 0.17x equals 120.6 minus e to the 0.17x. Next, we're just going to use simple algebra to solve for x. So we're going to add e to the 0.17x to each side, which will give us 2e to the 0.17x equals 120.6. Next, we're going to divide 2 from each side, which will give us e to the 0.17x equals 60.3. After this, we're going to have to use the natural log to get rid of e and bring the exponent down. So to do this, we're going to put the ln on both sides of the equation. The ln will cancel out the e, and then we will get ln of 60.3 equals 0.17x. Next, we will divide 0.17x from each side, which will actually solve our answer for x and give us the optimum number of days. So x would equal ln of 60.3 divided by 0.17. And when you calculate this out, you will get x equals 24.11 days. But you want an exact number of days, so we'll be rounding down to 24 days. So the optimum number of days for the job to last will be 24. So next we'll be solving B, which is to find the total income for the optimum number of days. So for this question, we will be needing the income rate equation, which is 120.6 minus e to the 0.17x. So we are going to be using what we learned from 15.5, which is the area between two curves. And we're going to want to solve the antiderivative of Ix by using lower and upper bounds. So the upper bound in this problem will be the optimum number of days, which will be 24, and the lower bound will be 0 because that's when it starts. It goes from 0 to 24. So we were going to want to put our equation next to the upper bound and now solve for the antiderivative. So to do this, we're going to divide our equation in half and solve for the antiderivatives of 120.6, which equals 120.6x, using the constant rule. And now we're going to want to use the exponential rule for antiderivatives, which is 1 over a times e to the ax. So in this case, it will be 1 over 0.17 times e to the 0.17x and multiplied by -1. So -1 over 0.17 times e to the 0.17x. Next, we're going to want to put these two together, and which will form our antiderivative equation. So the upper bound will still be 24 and the lower bound will still be 0. And we'll just add them together, so it'll be 120.6x minus 1 over 0.17 e to the 0.17x. Now we're going to want to use our equation from 15.5, which is the upper function minus the lower function. So we're going to want to plug in x and plug in 0. So to our equation. So 120.6 times 24 minus 1 over 0.17 e to the 0.17x. And we're going to want to subtract it using this rule. We're going to want to subtract 120.6 times 0 minus 1 over 0.17 e to the 0.17 times 0. And this should give us our total income. When you subtract these two equations, we will get a total income of $2,552.37. Next, we want to find the total expenditures for the optimum number of days. To do this, we'll be using our expenditure rate equation, which is e to the 0.17x. Now we're going to want to take a similar step to what we took for the last problem and take the antiderivative of the expenditure rate equation. We are also going to want to use the same upper and lower bounds because it's optimum number of days we're solving for. So, to find the antiderivative of e to the 0.17x, we are going to be using the exponential rule for antiderivatives, which is 1 over a times e to the ax. So it will be 1 over 0.17 times e to the 0.17x. 0.17 is the a value. So now that we have our antiderivative equation, we can plug in our upper and lower bounds to solve for the total expenditures. So we're going to plug in 24 for x and 0 for x. So after we plug these numbers in, we're going to get a total expenditure rate of $342.03. And that will be our total expenditures for the optimum number of 24 days. And don't forget our expenditure rate is in dollars, so label it in $sign. Now to solve B to find the maximum profit, we will use what they've already given us in the problem, which would be the profit is total income minus total expenditures. There's two ways you can go with this problem, and I will show you the easier way and the hard way. So first, we can use what we already have found, which would just be, since we already found the optimum number of days and the optimum number of income and expenditure on those days, we can just subtract those two numbers to find the profit. So this would mean that we would subtract $2,552.37 minus $342.03, and this would give us a total profit of $2,210.34. So now I'm going to show you guys the more complex way. And I suggest this way because it's a little more better practice for the upcoming exam. Solve this in this more complex way. We know that profit is income minus expenditures. So we can use, to find the profit equation, we can subtract the income rate equation minus the expenditure rate equation. And this will give us the derivative of the profit function. So we are going to want to keep the upper and lower bound the same here because it's still the optimum number of days, because we want to maximize. Then we want to subtract the income rate equation minus the expenditure rate equation. So 120.6 minus 0.17x minus e to the 0.17x. So now, if we combine our like terms and clean that up a little bit, we get 120.6 minus 2e to the 0.17x. So this would be the derivative of our profit equation. Now to find our profit equation, we are going to want to take the antiderivative of this equation. So we're going to use the same rules we already did. So the antiderivative of 120.6 equals 120.6x. The antiderivative of negative 2e to the 0.17x equals negative 2 times 1 over 0.17 e to the 0.17x. That is involving our constant for the antiderivative rule and the exponential function antiderivative rule. So now that we've found our antiderivatives, we're going to want to combine them together. So it will be 120.6 minus 2 over 0.17 e to the 0.17x, keeping the upper and lower bound the same. Now we're going to want to use the other rule we talked about, which would be the upper bound minus the lower bound by plugging them both in for x. So if we plug in 24 for x, we get 120.6 times 24 minus 2 over 0.17 times e to the 0.17 times 24. And we're going to want to subtract 120.6 times 0 minus 2 over 0.17 times e to the 0.17 times 0. This gives us the same number we found in the last way, which is a total profit of $2,210.34.